This video is going to present our work on winter conference on applications of computer vision. And the title is Learning to Adapt Clip for Few-Shot Monocular Depth Estimation. In our work, we explore the monocular depth estimation task using vision language models in a new few-shot setting, which aims to improve the depth estimation performance of pre-trained large-scale models by leveraging a small set of annotated samples. We recognize that images from different scenes have various depth distributions, so we design learnable prompts and learnable depth codebook to adapt the clip model for different scenes effectively. We evaluate our proposed method on NYU V2 dataset with only one image per scene for training. Our method outperforms the previous state-of-the-art method and can even be compared to fully supervised methods. Let's talk about some related work. The first is vision language models. This kind of models utilize extensive datasets to acquire representations that encompass the semantic comprehension of images and accompany textual description. And the second is the prompt tuning methods for VLMs. This kind of methods devise intricate prompts and incorporating adaptable context to extract task-relevant information from the encoded knowledge. And the last one is monocular depth estimation. Both machine learning-based and deep learning-based methods, which need lots of specific processed data to train, are commonly used in this mission. And there is a novel approach called depth clip. It combines with zero-shot training-free clip. It can estimate the depth directly. However, on one hand, the traditional methods are computationally expensive and time-consuming. On the other hand, presetting specific parameters in depth clip may lead to model performance that is strong in certain scenarios but suboptimal in others, which means poor generalization. So in our work, we try to address this important issue. This is a pipeline of our method. The textual encoder and scene encoder are directly from the original CLIP model with ResNet 15 backbone. The visual encoder is the CLIP's ResNet 50 image encoder, but without the final pooling layer. The file icon means the parameters will be updated during few-shot training. The first part is the learnable prompt. We turn the prompt text to learnable vector and then combine with 7 depth classes. The textual input will be as a form of learnable vector and depth classes. And all the text input will be put into the textual encoder, and we will get all the k-depth classes text features. The next part is about learnable depth codebook. We have few-shot training samples. Our samples are composed by taking one image from each scene class to get n class-specific features. For the input image I, it will go through the scene encoder to get the input scene feature. And then we compute the similarity between the scene feature of the input image and the class-specific features, which can help us to choose the most similar scene and choose corresponding depth bin from the depth codebook. And finally is to do depth prediction. For the input image I, we feed it into image encoder without pooling layer to obtain image feature. And then we calculate the cosine similarity between text features and image feature to get similarity score. And the score will be softmaxed to get the depth weight. And then we directly weighted sum to acquire the result of each patch. The depth estimation result obtained here is based on patches, and the depth of each pixel in each patch is equal to the value of the depth estimation result of the patch. This is our result. The table is the performance comparisons of our proposed methods and previous state-of-the-art methods on the NYU V2 dataset. The lower bound is obtained by randomly making prediction for each pixel within depth range 0 to 10 meter. We report the results obtained by previous state-of-the-art on fully supervised and zero-shot or few-shot settings. Let's make a conclusion. We propose a few-shot-based method that aims to adapt CLIP for monocular depth estimation. This approach focuses on striking a balance between training cost and generalization ability. Specifically, it assigns varying depth bin to different scenes, allowing the model to select the appropriate bins during inference. Furthermore, we introduce a learnable prompt to preprocess the input text, facilitating the conversion of easily understandable human text into vectors that are readily interpreted by the model. That's all for our work. Thanks for listening.